In this lecture module, we want to shift our focus towards how we go from a proto-scientific world to a world in which we have a normal science, a mature science that has a well-defined and reasonably well understood physical domain. The first step in this process is a recognition that there is a domain in the phenomenon, that there is a set of unities and regularities that potentially allow theorists to formulate dynamical and attributional models that can capture and unify those unities and regularities into a well-understood domain. Unities and regularities can come in the form of properties, dispositions, and of dynamical patterns of evolution. Without these things, one really doesn't have a basis for a scientific treatment of a domain. An example of a regularity or a unity in a form of a property would be the example of mass. All macro objects have mass. Radioactive decay is an example of a disposition. When a particular atom of uranium or thorium or so on is going to decay is a stochastic or unpredictable event. However, the rate of decay for any particular radioactive element is predictable over time. That is, how many atoms will decay in a given group over a period of time can be understood and quantified as a disposition of that element. Uniform gravitational acceleration in the Earth's gravitational field was thought, for instance, by Galileo to be an example of a uniform, unifying dispositional property of all matter. Periodicity, as quantified in the ideal pendulum law, for instance, is an example of a regularity in the dynamic pattern of evolution of a system over time. It has the additional property of unifying the relationships between arm length gravitational acceleration and the time that it takes for the pendulum bob to move from one end of the arc to the other. It also distinguishes that motion from mass. Other factors also influence whether, when, and how scientists cut up the physical world into domains. The interests and needs of scientists, oftentimes in the form of basic research without clear applications, are expressions of these means by which scientists shape how the world gets broken into physical domains. Applied science, or science that's driven by the interests and needs of society or industry, is an example of another factor that shapes the development and understanding of a physical domain. So, for instance, when we looked at the case of Galileo, Galileo's initial investigations were largely basic science. There's some applications to, for instance, projectiles, but for the most part, he's interested in how it is that objects fall, whether they fall uniformly or not. However, theorists that follow Galileo are driven to some degree by the needs of society and industry. The adoption of pendulums for instance, timekeeping actually accelerates the understanding of pendulum motion, beginning with Christian Huygens. The available experimental techniques and instruments will also shape how it is that scientists cut up and understand a set of physical phenomena. So, for example, Galileo only discovers periodicity in pendulums because he develops this experimental technique of using pendulums to compensate for the limitations of his temporal measurement instruments, i.e. his pulse or water clocks. So because he can't time the fall of objects very finely, he has to come up with a way of measuring the acceleration of gravity when it is tempered or mitigated by, for instance, an inclined plane or by the pendulum arm. The availability of modeling tools will also have a big impact on this. So Galileo was thinking about periodicity and about gravitational acceleration primarily through geometrical means of representing and quantifying. Today, of course, we use calculus. Prior to the use of calculus, and people used algebra and so on. Finally, the availability of data. Before one can start to formulate a domain, one has to be able to recognize those unities and regularities of properties, dispositions, or dynamical patterns. And that means one has to have sufficient data, familiarity with the domain, in order to be able to identify unities and regularities. Our primary illustrative example of how researchers delimit a scientific domain in this chapter has been our discussion about Galileo and how he initially begins with a domain having to do with uniform gravitational acceleration, in which the ideal pendulum law plays a part, and how, as people's understanding of pendulums and of oscillating systems generally started to evolve, that model gets moved over first to a physical domain having to do with harmonic motion, then dampened harmonic motion, and finally to oscillating systems theory. In the next chapter, we'll look at another example of theorists attempting to limit a domain when we look at how ancient Greek thinkers tried to develop the notion of a soul and to determine or delimit the sorts of phenomenon that they wanted to associate with that notion of the soul. As we'll see, initially they included phenomenon having to do with the distinction between being animate and inanimate, and phenomenon that had to do with the distinction between being living and non-living, as well as phenomenon that had to do with the distinction between being a mental entity and not being a mental entity. In our next lecture module, we'll turn our attention to the development of an experimental tradition.